So we had a lot of inscriptions in our event. So this is a 2-week event. We have 164 participants during the 2 weeks. 104 in the school and 114 in the workshop. So I have some statistics for you. So from the 164 participants, along distributed in the 2 weeks, we have 105 freshmen and freshmen, so people that are here for the first time, and 58 senior people, people that have been here in our previous editions. So from the 164 participants, so all of you are here, right? 164. Some people will arrive in the next week for the workshop. So from these people, more or less 40 have been here in 2019, 30 few in 2017, and so on. But if you look at the people that are here in this week, so we have the proportion of fresh people is much bigger, right? So we have 104 students in the school, from which 83 are fresh and only 21 have been here in previous editions. This is the This is the schedule of our school for this week, right? So we have 4 courses. We will start with Nadja today, and we have 2 poster sessions, right? So you don't know in which poster session you are going to present. You have to go to our office here during the lunchtime and choose one of each, right? So you can choose. We have 30 spots for the poster session number 1 and 30 spots for the poster session number 2. So you can choose which one you prefer to present, but we have up to 30 spots in each one, right? So during the lunchtime, you can come to our office and choose the session you would like to present your poster. For registration, like to take your badge, during coffee breaks and lunchtime, you can come to our office and take your badge, right? And we have a few announcements, modifications. So if you look at the program in the website, it's already changed. So Fernando Brandão will present like two lectures tomorrow, and we have replaced some of the lectures, right? So as always, we have our cachaças, which is our souvenir. We have two flavors of cachaça. We will start selling it tomorrow, not today, right? The cost is like 15 reais for one bottle. This is the little bottle, this bottle here, right? And 40 if you want to take 2 bottles. So tomorrow we will start selling it. And this is our lectures for this week. So we have Glaucia Murta, Nadja Bernardes, Richard Wang, Fernando Brandão, Esteban Sepúlveda, and Steve Walborn. So we are going to present us 5 courses during this week. So we have Wi-Fi as well, if you haven't seen it here, so you can log into this network. And the first course will be given by Nadja Bernardes. Nadja is professor at the University Federal of Pernambuco in Recife. She has been my colleague in Belo Horizonte. We studied together in Belo Horizonte, in UFMG. She was also my colleague, organizing Paraty in 2019. And she's going to present us a course on quantum non-Markovianity, characterization, detection, and application. So during the courses, you can ask questions, and we will pass the microphone to you, So the duration of each lecture is 1 hour and 15 minutes. So you can ask as much questions as you would like to. And now I will pass the microphone to Nadja, so that she can start with the lecture. Thank you, Nadja.
Just reinforcing what Danielle just said, this is cool. Please make questions, but when you want to make a question, just raise your hand and we'll do our best for the microphone to appear in your hand. Remember, it's being recorded and it's important that everyone hears your question. So enjoy Nadja's lecture and make questions. This is a very important part. It's a very important contribution that students can give to the school.
So, good morning, everybody. First, it's a great pleasure to be here today. As you saw, I came to Paraty as a student in 2007, and then as a researcher, then as organizer. And today is the first time as a lecturer, and I'm very happy about it. So I'll be telling you about quantum non-Markovianity and stuff. But before I really talk about the subject, I want to tell you a little bit from where I'm based now. So I'm from the Federal University of Pernambuco. Just for you that don't know exactly where those cities are, we are more or less here, more or less, okay? And Recife is here on the coast in the northeast part of Brazil. And well, we are famous about the carnival. We have one of the best carnivals in the country, which means like in the world. And we have very beautiful beaches, and we are based in this Centro de Ciências Exatas e da Natureza. We have a quantum information group there. We are doing theory and experiments. And we are a good graduate school, and we are looking for master and PhD students. So if you find interesting the things that I will tell you this week, so I invite you to come to visit us, and we can talk during the coffee breaks and so on. Okay, so after the advertisement, we can start then with the lecture. Well, I divided this course in 3 questions. So the first question is, what is the quantum Markovian process? So just to start, who has already worked or did some courses about open quantum systems and these things? So you can raise your hands. Okay, good. Not so many people. Marcelo, great. So the first lecture today will be about what is the quantum Markovian process. Okay, this is what I will call day 1. And we will be then looking to the characterization. Then the second question will be, if a given process deviates from Markovianity, by how much does it deviate? So we'll be talking about detection and quantification. Oh, this is day 2. And the last question is, what is it good for? Okay, so then you day 3. And in fact, I will be talking about applications. And I want to give you some toy model, which I think is useful for studying quantum non-Markovian process. Well, I have some references here. I put here some reviews. So this is a very typical reference, which is this Rivas, the Plano review. I like it very much. So the things that I'll be telling here, like most of the things, you can go there in this review and you'll find reference there. So there is also this review from Vegas and Alonso. they present non-Markovianity more as like not so intended to the quantum information community. It's more like really physics community, so it's a little bit different. The things they are more like connected to the experiments than the first review, but I think they are complementary, these two reviews. And also there are these two other reviews, non-Markovian quantum dynamics, what does it mean and what is it good for, which is presenting already like real experiments more connected to quantum information. Okay, so these are the references that I will use in this lecture. So okay, I will be talking about open quantum systems. So I have a typical scenario. I have a system of interest, which I'm calling system, but of course everything is a system, the big thing is a system, but when I'm saying system is the thing that I'm interested about, okay? Which is connected to the environment, and the environment is the thing that I'm not interested about, that is like disturbing what I want to do with my system, okay? So I can think about this environment. It doesn't have to be a bath, it can have the properties of a bath, but it can be that it's just another quantum system, just another qubit, or it can be that it's like, I don't know, thousands and thousands of qubits. But I can give it like different descriptions. I can think it as a classical system, the environment, okay? I have like as a quantum system, or I have a third description that will be like quantum system plus measurements. And this will give me like the description of quantum trajectories, which I will not talk in this course. Okay? So we have this third way of describing the dynamics of open quantum systems, which is my system is interacting with another quantum system, and I'm monitoring this other quantum system, and I will get some information about the system, but I won't get into this description, okay? I just wanted to tell you, because then you know there is this other alternative, but I won't talk about it. So what do I have here? I always consider that I'm describing then a big system that is acting on a Hilbert space, where I have then the Hilbert space of the system and the Hilbert space of the environment. I can describe the evolution of this big thing with a Hamiltonian, which is, there is a part that is just acting on the system, and another part that is just acting on the environment, and I have interaction Hamiltonian, okay? So these are the basics of the beginning of my description. So what I want to convince you here during this course is that, is it big enough? For you that are yes, okay, good. So then depending on different things, so depending on the interaction that I have between my system and the environment, which can be, I would say, weak or strong, or the characteristics of the environment, which can be, if it's correlated, the particles of the environment, or if I have big initial correlation between between system plus environment, or if my environment has some structure. I will be able to tell if the dynamics is Markovian or non-Markovian, okay? So these are the things that I will still define, but what I will be looking is always this character of the dynamics. And what is connected to this Markovian or non-Markovian is usually some memory effect. So when I have a Markovian dynamics, I don't have this memory effect, and I will be more precise about what I mean. But this is already something you can keep in mind. No memory effect. And in this non-Markovian, I have some memory effect. So, as Schneider already showed us, Paraty is a very non-Markovian event. So you can see that when people come here for the first time, the probability that they will come again is very high. So I was just searching for pictures, and then I found this picture here about the first Paraty in 2007. So you can see Marcelo there, he's Leonardo, will be here in the next week. Gabriela couldn't come, but okay, she came also many times. So we have these things. Paraty is a very non-Markovian event. So then going back to this, well, let's then define these things better. But still to motivate a little bit why I want to, why I think it's important to look to this Markovian and non-Markovian stuff, I think we have to answer, why is it important to study open quantum system dynamics? So, I forgot to put a picture, but I think you have this in mind. Like, when we look to the quantum computer, for example, the IBM Sycamore processor, it has kind of, I think it's nanometers, the size. And this chip is kind of the big room full of controllers for this processor to work. So what we see is that quantum systems, they are proving to have an advantage for some tests, but it's very difficult to control all these quantum systems in a way that it works in the way that we want. So to understand the dynamics of an open quantum system is essential to be able to really do the things that we are promising in that we have been promising in the last 20 years. So one of the things is that because of this interaction of the system with the environment, we lose the quantum properties that we want. So then we can see this description, like the motivation from two perspectives. So we want at the end to be able to build models, physical models, to describe this interaction. And one of the things is that we want to describe and understand this quantum classical transition. This is not what we will do in this course also. I'm starting saying everything that we won't do. And the other thing, is what I think is I'm more motivated, is, well, when we describe this interaction, and we can then possibly control. So imagine we know how this interaction is happening, and maybe we can do some engineering in the reservoir, and we can control better this interaction, and then we can possibly avoid with this these damaging effects. Caused by this interaction, and we will also see that depending if the dynamics is non-Markovian or not, we can even explore this interaction to have some advantage, to take some advantage about this interaction, okay? So at the end, what we are trying to avoid is this decoherence effect. So, how does it work? I will give some example about how you can understand the coherence when you have an open system. It's kind of artificial example, but just to give you an idea what it's doing to my quantum state. So imagine I have a qubit, and the qubit is interacting with some environment in a way that, okay, I start with my qubit in state 0, in my environment in state E, and it evolves to some, okay, when they interact, the environment gets some information about my state, so it will go to state E0. Okay? The 0 is just a label because it interacted with the quantum system that was in state 0. So it can also be that I started with my qubit in state 1, and then it goes to the environment, and then up in state E1. Okay. So I can also start my qubit in a superposition, something like this, and it will interact with the environment, and just following this receipt that I showed you, well, it will go to something, I don't know, which is a superposition of E0. So you see that it's very artificial because the qubit is not changing, just the environment is changing because of it. This is just an example, okay? Well, it gets in some information. So what happens then if I just look to the state of the qubit of my system? I have this, okay, I will then, since I'm just interested about the system, I will trace out the degrees of freedom of the environment, okay? This we'll be doing all the time when we can look to the bigger picture, and then we will just treat it as an isolated system because the big thing, it's not interacting with anything else, and then we trace out the degrees of freedom of the environment, of the Markovian environment. So I will say that the system, this is already telling you a little bit about one of the possible descriptions of open systems. So I evolve the big thing, which is I'm labeling as system plus environment. And then what I see here, I have the following state. So we can see that in the diagonal terms, we just have this modulus alpha squared and modulus alpha 1 squared. But on the other, the non-diagonal terms, which are related to the decoherence in this basis, we have, it appears, these elements that they are connected to this, how the environment is changing. So if the result of the interaction is putting my environment completely different, if it interacts with qubit 1 or qubit 0, imagine that the environment is going to orthogonal states or to very different situations, which I'm measuring it as like with this orthogonality. We see then if they will go to orthogonal state, at the end what I will have is a state, something like this, where I don't have anymore these non-diagonal terms. So I'm killing coherence, okay? That's why I call this process, okay, decoherence. This is, okay, I'm killing coherence, so I'm telling you, maybe someone will tell you during this week, but I guess most of you know that coherence is something important for doing quantum information processing, and it's also connected to entanglement, okay? So if I'm killing coherence, I can also do the same play with a Bell state or maximally coherent, maximally entangled state. And it starts with something. Okay, here's just one of the example of the Bell states. And if I have a process similar to this, I will end up with something without the non-diagonal terms. So I'm just killing entanglement. Okay? So this is one of the points why it's important. We want to avoid these decoherence processes. Is it clear? Like, if you want to make questions, you can interrupt me at any time, okay? Good. So, how can we then, yes, Nina, wait for the microphone. And then I can drink some water.
I don't know if this is a silly question, but I was just wondering.
No silly questions here, all questions are important.
I was wondering about some of the passages that the ups. Can you go up a little bit? So yeah, I was wondering about, because it starts with alpha 0 plus beta 1, and then it changes to alpha 0 and
yes.
alpha 1. Does it change the
No, it's just
coefficients?
okay, let me put it.
Okay, I was just wondering if the coefficients changed or...
No, the coefficients can change because of the interaction, yes,
They can change.
They
Okay,
can
that was
change.
just my question.
It's just an example, like we have some freedom of doing. Of course, you can tell me, well, you are just choosing like an example where you are able to prove your point. Yes, I did it, okay?
No, I was just wondering if the coefficients can change or not. And the second one, just wanted to confirm that is the partial trace over there?
Yes.
Yeah, partial trace on the environment.
Yeah, that's good. Okay, thank you. This was a mistake. Yeah. He's just environment.
Okay.
Thank you. Yes. Yeah. It's a partial trace. Any other question? Okay. So then, just formalizing a little bit these things, how can we describe the dynamics of an open quantum system? How is the description? Well, if I just have an isolated system, we know, well, quantum mechanics course 1, undergrad course, you already saw Schrödinger's equation, which here I will write it for a mixed state. Then it's called Liouville von Neumann equation, but it's just the same thing. For an isolated quantum system, I can write the evolution. Well, I did it before without explaining it, but I'm sure you know this. Where this unitary operator is related to the Hamiltonian. Okay? I'm not considering Hamiltonians that are depending on time, okay? So I will just keep it. I won't work with Hamiltonians depending on time, okay? For an open quantum system, I can think the same way, as I already told you. I can just consider my system and environment as the big thing. And now I won't do it wrong. I just have this partial trace in the environment. And what I'm considering is that initially, system and environment, they are not correlated. Okay? This is important. So this is an assumption. My initial assumption is that my time 0 is when the two things are not correlated, then I turn something on, I turn the whatever laser on, something on, and then they start to interact, okay? Well, this is nice, I can do this, but look that, to do this description, you have to know the state of the environment, which is not practical. Usually you don't know the state of the environment. Imagine like your big room. You have to describe all the particles in your big room and to be able to give this description. So formally, it's everything okay. You can do this. But if you just think as like, with a little bit more experimental point of view, you will say, well, Nadja, this is impossible. You won't be able to say what is the state of the environment. So we have some other descriptions, which are equivalent, but they can be more practical from a realistic point of view. And these other approaches I will divide them into groups. One group which I will call axiomatic. So I still don't have a clear physical motivation for it to happen, but I will tell you that I have this map, which is kind of a mathematical operation, and this will solve my problem in a different way. And I have the other description, which I will call microscopic. So the microscopic is when I have some information about my environment. I don't know all the state of all the particles, but I know something about my environment. I will use this information. So let's start then with the macroscopic. Yeah. So, let's start with the maps, which I'm calling axiomatic. Now that I'm getting more relaxed, I can do the things that I like to do. At the beginning, my letter was, ooh, okay, so. It's funny. Someday we will be here and then you will know what I'm saying. So.
You're not asking for a cachaça.
Yeah, I do have here. So the maps is then it's just an operator, which I will call here phi t, and they are acting on operators from one Hilbert space to the other. Okay, they don't. This is something that I'm considering that it doesn't have to be like this from a Hilbert space with dimension whatever to the same dimension. It can go to different dimensions, but just to simplify the problem, I will just consider the same dimension. Okay, and the dimension in all the three lectures, the dimension of the system is D. I just have to define this because sometimes I will just use D and then you know, okay, D, she said that the first lecture is the dimension of the system. Because sometimes we will look to smaller things or bigger things, okay? So, how is this map acting? So the map is acting on the state of the system, which is initially, I'm saying that is in time 0, and it's taking to time t. Okay, so the map is acting on my initial state and taking this initial, evolving this initial state. So I'm working with density operators. We know that density operators, they have to fulfill some properties. So the trace of rho is 1. And the eigenvalues are positive and or 0, so it is a positive operator. One other thing that my notation is a little bit confusing, but I will just call your attention about it. Here's time. Here's system. Okay, the time for the density operator is containing in the argument like rho s of t, okay? And for the map, I'm putting it in the subscript. So just don't confuse it, because I want to tell you system, because sometimes I'll have the environment, and to make this difference between system and environment, I use this rho s, okay? But it's not connected to time. The time is here inside. Well, since I'm taking density operators to density operators, this map has to fulfill some properties, which is, it has to be what we call completely positive and trace preserving. what we also call CPTP. So I will say a lot, I will say this many times, CPTP. Well, why? Trace preserving, because as I said, the density matrix, trace 1, I want it to remain this, so this is just connected to the probability that I will find my quantum system in a state or another, and the sum of probabilities, the total probability is just 1, and I don't want to change it, so I still have this trace preserving condition. Positive, as I said, I have a positive operator, I want it to be still positive, but why completely positive? So it can be that my system is entangled or correlated to some other part, and I don't know, and I want to guarantee that even if I act to my map in this part here, that this big thing is also going to something that is still a density matrix. So at the end, if I have this map, this is a positive map, I say that this guy here is completely positive, okay? It's just the extension of the map in a larger Hilbert space is, if this is positive, then phi t is completely positive. Cool. So how can I represent then this map? I know that I have a map that is taking my state from 0 to t, but how can I represent it? One way to do it, well, let's go back to the description of I know the environment, which is also called the Stein-Spring representation. And then I can see, okay, I will just do this partial trace. I will choose some basis for my environment. This is not good because it's the same level of the... And then I can do this partial trace using this basis. Wow. I'm also deciding to write, okay, here is the radius system. It's in a diagonal form. I will just write E. The U was missing. The dagger. Let me just put is. Is it clear what I'm doing? I'm just taking the partial trace, and I have represented the system, the environment state in its diagonal form, or in the basis that diagonalizes it, okay? So what I can do then, this U operator is acting on the both space, in the system space and in the environment space. So, but I can't just, since the system and the environment, they don't have the correlation at the beginning, I can just rewrite this as square root. And this is just some number, like a positive number, so I just can change the place of it, but I think to be clear, so what I mean. So I'm just reordering things, okay? Is it clear what I did? If not, I can go slower. No? Okay. So at the end, what I did is just I put this here because the system is acting on a different Hilbert space, so I can just change. And this I just kept the same. And lambda is just a positive value, so I can just divide it in the square root. Okay. Then I can identify here something that I call the Krauss operators, which is, I will change a little bit the labels. Here was I J from 1 to D, and now I have something that is from 1 to alpha squared, or alpha D squared. But it's the same. I have two labels that goes from 1 to D, now I have one label that goes from 1 to D squared, okay? Where I have then this K alpha is just related to this guy. So as you can see, my map, this is a way to get the cross operators, but it's not the only way. So I will comment on this, but I always have, when I have a map, a CPTP map, it always has a cross representation, and the only thing that these cross operators they have to fulfill is that the sum alpha daga, alpha, it has to go to identity. If the map is trace preserved, completely positive and trace preserved. You can have a map that is completely positive but not trace preserving, but then you can kind of do it by hand at the end, you can correct this trace preservation. Okay, we have another question here. Cool.
Just one thing about the calculation, why d squared in the, why it became d squared in the sum?
Because before I had two indices, I and j, going from 1 to d. Now I have just alpha and it goes from 1 to d squared. Like, before I had like two sums, now I have just one. Okay?
And just another question that is a technical one. These nodes, is there a way for them to be available for us later?
Yeah, sure. We can put in the website. I think we can, no? Yeah, cool.
Let me make a provocative question, Nadja.
Yes.
Is it clear for everyone that this bra, I, you, another you, cat, is not a number? For the first time I have seen this, I couldn't understand for something like 2 hours, and you were facing this.
Guys, for sure you, like, many of you already saw it, but it's not a problem if you didn't have understood, because you understand, because it's kind of these things take some time. So if you want to make questions, don't worry, just do it. The thing, yeah. I don't have to finish all the things that I prepared. Yeah.
Hi Nadja, I have a question. This map represents the current process of the system with the environment.
Very good. This map represents all the physical process. Everything that you like. The coherence process, yes, but also if it's just a unitary, you will have the cross operator will be the unitary operator. Okay, so they coincide. So I don't have any, it's just general enough for all the physical process. Maybe this is my take-home message. Yes, still my take-home message. All physical process are represented by CPTP maps, and they have a cross representation for. Any other question? Yes.
Hi, I was wondering about this U. It is not clear for me why you can write the omega environment as a sum with only one index.
Okay.
Can you always, for any basis phi find a corresponding U?
So this is the state of the environment, and it's just a density matrix, and as we know, the density matrix can only be diagonalized in some bases. So the Uj is the basis that is diagonalizing the environment state. And here, just not to be like too specific, I have chosen another basis, but it's okay. I was writing environment A and D, and now I just to make it short, I wrote E.
So maybe I made a mistake in reading. So in this line, in the sum, that's a sum over Uj. Not phi j.
Here, you mean?
No, the line above.
Up here?
No. Up.
Ah.
Yes.
His
There's a
I
sum of a J,
and his J.
and then there's a lambda, and then the next letter.
UJ.
Ah, okay, that's me. Okay, thank you.
So, yes, sorry for my, yeah. You get used to it. This is just the beginning. Here, questions?
Hi, Nadja. Just one question. This is quite general. The only assumption that you are making is that the initial state is uncorrelated.
Yeah.
But if you start with a correlated state, this you can get a CPTP map from it or not?
Good question.
Because it's very strange to me how is this initial correlation.
Well, it's not straightforward. Like you don't get necessarily a completely positive, but you have ways to still save your day. Like there are people doing descriptions when you imagine it like kind of the universe. Like we are already correlated. We cannot just say, let's go to the time, the Big Bang time, and you will go into this time where you don't have any correlation. So there are situations where you need this description. You cannot assume that you don't have correlation. But it's not so easy, this description, okay? But there are like alternatives. But usually we just consider that you don't have correlation.
Perfect.
But you can just, the only thing that I think people don't give up is that is a linear map. But completely positive, sometimes people just, they don't assume it, okay?
Thank you, Nadja.
Yes?
Following the question from Terra, it's not clear to me how it's possible to do this product because the dimension of the matrix U is different from the state UJ. How it's possible?
Yeah, I forgot to answer the Terra's questions. This U, you are completely right, is acting on the Hilbert space of the system and the environment. But now this is a partial trace. So imagine I have some big matrix and I'm just I'm tracing like one of the degrees. So I'm reducing this big matrix to some smaller matrix. So it's still an operator, okay? So this is why the representation of the Krauss operator are matrices. And there are matrices that the only thing that they have to fulfill is the sum of K alpha rho. This is wrong, sorry. No, this is correct, but the condition is not this. It's this here, okay? The only thing that I need is that these matrices, they fulfill this. But it's a matrix, it's not a number. Because usually we see this as representing the elements of the density matrix. But in this case, the U is acting on a bigger Hilbert space, or a larger Hilbert space, okay? Are you convinced now? Cool. Any other question? Good. Okay. One thing important here is that, okay, we have chosen some bases here. So you see that the Krauss operators is depending on these bases that I have chosen. So I don't have just one set of Krauss operators that describe my map. I can have different sets and they will be equivalent. So the Krauss operator is not a unique representation, okay? So I can have a map, I don't know, the polarizing map, and I can describe it with different Krauss operators. So then just summarizing this first part, we have this, okay, just the take-home message, which is the things that I really want you, like if you didn't grasp all the details of the calculations, it's not a problem because my notes will be available so you can go back to these notes. But I think there are things message that I want you to go home with them. And the first one is all physical process are described by CPTP. Well, the trace preserving, maybe you have to do something by hand, but at the end you will get it, okay? Maps, and can be represented by cross operators. And, well, I told you that I wanted to escape a little bit from knowing the state of the environment and, well, we have this map and blah, blah, but at the end, to prove what are the cross operators, I use the environment, but this is not the only way to get the cross operators. So one way to find the cross operator is to go to the lab, and I will just do some tomographic in the state, so I will find what are the initial states. Then I will do some tomographic process at the end, and I will find the final state. And in fact, I will have to do well, because this is what I'm telling you is the tomographic of the state. But you can do similar thing for the process. So you can just, in a smart way, measure some operators, and then you find what this evolution is doing with this operator. And if you find set, or like in a smart way, you find the set of important operators, or kind of a basis, but it's not a basis, you'll be able to do this and find the cross operators. Okay? So just measuring, we call this the tomographic process. Okay? But it's similar to what we do in the states, with the tomographic of states. So you can go to the lab. Okay, I'll start. I didn't want to really explain, but now I got confused. So I will just say very fast about what is this tomographic of states. So you know for 1 qubit, I can represent it in the Bloch sphere. So this R is this Bloch vector in the Bloch sphere. But how do you measure this? Can anybody tell me? How do I measure this? R, X, R, Y, R, Z?
No clue.
You take the trace against the poly operators?
Mm-hmm. I just measure Rx is defined as the expected value of trace. Okay, so I know what's the observable that I have to measure. I have to measure sigma x, sigma y, and sigma z, the Pauli operators. Okay, so for a tomographic process, it's a similar thing. I have to know what are the operators that I have to measure. I will be able to tell you what are the cross operators. So I don't need to tell you anything about the environment. Okay? Cool. So now going to the microscopic description, which is when I know something about the environment, I will then describe this. Just for me to be sure, I started 9:15. Is there? When did we start? 15 minutes? Oh, shit. No, but we started later. Let me check here. I cannot read.
20.
Okay, 20 minutes. Like, good. So, then the microscopic description will be given by these master equations, which will be what we call in this Lindblad form. So master equation is connected to how something changes in time, and I will look to the derivative. So again, if I just have the whole system, this is another description of the evolution, which is called the Liouville von Neumann equation. Okay, so just have the total system. Now, I'm just looking to the system. So, as I told you, I can do it using the map. And if I just want to look to the first derivative in time, then I will take the derivative of this thing here. And I will represent this derivative of the map applied to the initial system as the phi point. And okay, and I can rewrite this as.
I'm sorry, Nadja, have half an hour.
Ah,
Half an hour.
okay, cool, I'm fine. So I'm just, what I did here is that, okay, I assume that the map has an inverse, which is not always true, but let's, we don't have to go into this detail. But assuming that it has, what I apply is the inverse in the evolved state, which is just from 0, okay? Why I'm doing this? Because now I can identify what is the operator. If I'm just looking to the derivative of the state, how it is changing in time, I will identify it then, I'm calling another operator here, which will be this guy here, okay? And this we call the generator. It's not a CTTP map, it's a map, but it's another kind of thing, okay? Generator or super operator, some people should call it. Because it's connected to the derivative. It's not only taking density operators to density operators, it's taking density operators to the derivative of density operators, okay? And if it has a special form, it will be called Lindbladian. And this is what we want to write. So I will not prove it, because I think we are, like, it's enough from proofs I already did for the cross operators. But the form of this master equation, when it has this Lindblad form, is this here. So you see that I still have something similar to what I had when I just have an isolated system, which was this first equation here. Okay. You all saw if you just worked with density matrices in your quantum mechanics courses. But now I have some other parts. Oops. Which is related to some operators here. Okay, so just to be a little bit formal, the Hamiltonian we know is Hermitian, okay, and LK are arbitrary operators, and it's important that these gamma operators and gamma k, they are rates, they are not operators, they are just numbers, and they have to be positive. Okay, this is what we call the Gorini-Kosakov-Sudarshan Lindblad equation. Then just let me write this because it is important. This Gorini-Kosakov-Sudarshan, they got into this, they published this equation where they wanted to say how can I describe open quantum system dynamics with master equations. And Lindblad also got this equation independently, but it was almost in the same, I don't know, some months close to each other, but somehow we say it more as Lindblad equation as Gorini-Kosakov, but to be fair, like they all published this result very close. It's not the same formulation, but it's able to show that it's like equivalent the results, okay? I will say theorem because we can prove it. Yeah.
So just to make a clearing point, I think when you use the braces, like by the end of the equation above, for the Lindbladian, it looks like it's supposed to be a nested commutator, but it isn't, right?
This thing here?
Yeah, there's like a brace, and there's an expression.
This will be just AB is anti-commutator, I think people call it, no?
Okay, but from the outside, you have like a brace from LK rho.
This?
Yeah, this is
no, it's, oh shit, okay. Let me put this as...
Oh, okay, it's not
it's not a comma, no, not at all, no. It's because this comma is kind of disturbing, no? But this guy is this. And here just have a minus. It's just some bracket. Okay, cool, yeah. No, the commutator is just here, H and rho. Any other question about my messy... Okay, well, I haven't proved anything about how we arrived in this equation, but something that I want to tell you, and these are the things that it's important for my course, is that to get to this equation, what they show, or it's possible to be shown, is that the map, so now I'll be connecting these two descriptions, okay? The map they have to fulfill the semi-group property. So not all dynamics can be described in master equation Lindblad form. And what is the semi-property is that the map can be divided. And there is something that my notation is also not, maybe it's not so clear for you, it's just, I can represent it like from the time 0 to time t, sometimes I put this comma, and when I'm omitting the 0, it means that it's from 0 to time t plus s, or from 0 to time, okay? Sometimes it's just omitting this t, the 0, sorry. So then I can write this map, I can divide it where for O, T, S, so if the map can be divided in two other CPTP maps, the total map is just the action of from one map until time S and another map until time T. I say that I can prove it that the master equation has this form here. So this is the semi-group property. So just to give a little bit of, since now I have the time that I can, okay, let's keep this. No, okay. A little bit of intuition about this Lindblad equation. Well, let me think about what would be the cross operators that I need to have a master equation in this form here, okay? So now I'm connecting this to descriptions. So I will consider that I'm looking to some evolution in a very small time because I want to connect the map with some derivative. So I will do the thing that mathematicians, they don't like, is just to kind of open the derivative and start to taking the delta t to one side to the other, okay? Like, that is suffering.
Dancing with the
I'm not the first and not the last one of doing this. Yeah, with some dance so that you don't notice it. Well, but then I'm just looking to the evolution from time t to time plus delta t, will be then the map acting in rho t. And as I said, okay, if it's a physical process, it has a cross representation. And what I want to find is what are these Krauss operators that gives me this Lindblad equation, okay? So then what I will assume is that since I was looking to master equations, so I had dt, okay? Then I will go from here to rho t plus delta t. It will be, I will assume that it will be like something rho t plus delta t. Is it clear? Just kind of open the derivative and the delta t on the other side. Yes? So good. From here, I can identify how is like my Krauss operators, they have to look more or less. So one of them just has to be identity because it's connected to rho t. What I'm doing, guys, I'm just comparing this equation with the master equation that I had before, okay? So I have that one of the Krauss operators, which I'm labeling with 0. Yes, let's put it here. It has to go with rho t, and the other has to go to something that goes to delta t. So this will be alpha. Okay, just different label. With this, I can identify then my K0 as being identity plus one will go G delta T, and here alpha. The same operator that appeared before. And I'm always consider this delta T small in a way that in terms of second order, I will just put it away. Okay? It's just an approximation that works in the first order. So then just comparing this with the Lindblad equation, what I see is that, okay, I have to make some choices about G, which is this operator G. And for this to work, I will choose G equals to F minus 1H. And F will be the thing that I had before. And we will see, okay, just let me replace it, all these things, and we will see that we will go with the master equation in the Lindblad form. So what I do have here is that I have a Krauss operators that it's most of the time it doesn't do anything because the part that I have this G is going with delta T, which I already told you that delta T is small, and another K alpha that is going to be square root of delta T. Okay? So then what is contained here is the important information is that to have this Lindblad equation, the interaction with my system, with the environment, has to be something like the interaction, it doesn't have to be, it cannot be something like very strong. So if I just look to this interaction in very small pieces of time, this interaction is weak, okay? So it's weak in a way that sometimes the environment don't even change its states. Like the environment is the swimming pool where you pour some water and the swimming pool is just there. Okay, my temperature is just the same. Okay? So this is something like, I told you that I will give you a microscopic description, assuming something about the environment. I haven't told you these details, but I'm just trying to show you, look into these Krauss operators. So what I have here is just an interaction where, well, most of the time, or the probability that nothing happens is bigger, okay? So then the interaction is just changing a little bit, the state. And that's what we see, because the state is rho t plus delta t. It's very similar to rho t, okay? So then just replacing everything in the equation, I'm already Okay, this is K0. Okay, I just replaced K0 and K alphas. And then replacing G, this is not T, this is delta T. What I have here is rho T, just from the identity, then I have delta T, G rho plus rho G, plus delta T, and this will give me rho T minus 1 delta T. H rho, because I have chosen G to be F plus minus 1 H, so, okay, plus delta T, so the mass equation in the Linkler form is already appearing. Is it clear that I recorded the same equation? Okay, I won't do the whole thing. But as I said, typical assumptions to get this Linkler equation are weak interaction. So it works for systems where I have weak interaction, which usually is called the Born approximation, and short correlation times. Which is called Markov approximation. So, as I said, the map, it has to fulfill this semi-group property, and this is connected to this Markov approximation. Well, I wanted to tell about master equations because they are very, people use it a lot to describe the dynamics of open quantum systems. But you will see in the rest of the course, I won't be really talking about master equations. I will just talk about maps. So this is almost the last part that you saw, master equations. So if you have questions about master equations and Linkler form, now it's the time. And then I will go back to. But I had to say about it because it would be kind of strange to make a course in non-Markovian stuff without talking about. Yes.
When you first mentioned this type of description, you said that you used this when you had a little bit of information about the system. I think it wasn't very clear to me where this information comes in and how do you would get it in practice.
Okay, yeah, maybe this was a problem of my description because I started with this, but here, when I'm assuming this, it's kind of, I'm assuming that the system is not really changing a lot in one small piece of time. If I have a very strong interaction, this won't be possible. Okay? The other thing which is more difficult just to show in a simplified way, but this master equation, it's possible to show that it's connected to maps, that they have to fulfill this. And this is what it's connected to this Markov approximation. If the environment has a lot of correlation inside, so when time is passing, the system will get, the system can lose information to the environment, but it will also get some information back, and then I cannot give this description. At the end, what happens is that in this master equation, it will appear like the coherence rates that they are negative, which is kind of strange because rates, they are usually positive, okay? So you are trying to describe something that you are not supposed to. But this part, I was more informative than really, because that's the problem. That's why I haven't done this. to make a full proof about the master equation, I would have to choose some scenario. And I didn't want, I still wanted to keep it general, okay? So if you just go to this Breuer's book, The Theory of Open Quantum Systems, you'll see it gives the proofs of master equations for many different scenarios. And I just wanted to keep it general. Any other question? Cool. So now we can just go to the last part of this lecture. And I told you that to get this master equation, I need this, the map has to fulfill this semi-group property, and I will relax a little bit this property. And I want, because the semi-group, I was talking about two maps. Here. So, if I want the evolution from 0 to time t plus s, I would need the evolution from 0 to s, and another map that is kind of from 0 to t. And now I will do something which is, I just want the map to be divisible, which will be I'll put this here. So, I want the map to fulfill this divisibility condition, which is, I want my whole evolution, it has to fulfill this. It has to be divided into other CP maps. One from time 0 to s, another from time s to t. So what happens here? If I have here, if I know what is the state of the system in time s, I just apply this map, and I will get the state in time t. So I don't need any information about the beginning. If I just have the state, you tell me at some point of the story, I just can tell you what is the state at the end or at some other point of the story. Okay? And with this, we are able to show that this condition, I also get a master equation in the Lindblad form. Master equation. And the only thing that changes is that my decoherence rate is still positive, but it can change in time. Before it was just some number, fixed number. Okay? Now it can. So, I have then a connection between maps, master equations, and now I will start to give names to these things. And when the maps, they fulfill the divisibility condition, I say that this dynamics is Markovian. Okay? To describe. And why is that? Well, just let me remind you about what is the name Markovian and Markovian used in classical systems. So I have for a classical system, for classical stochastics, process. I say that the process is, imagine that I have a chain where I have a variable x that can take values xn in time tn. Okay? And I said that the process is Markovian if the conditional probability of x assuming the value xn, which usually depends on all the steps before, if it just depends on the previous time. Okay? Which means if I want to say the probability of x assuming the value xn at time tn, okay, the label n is always connected to this time. I just have to know what was the probability that took the value x n minus 1 and this conditional probability. Okay, one very common example about Markovian process is the random walk. Okay, so then, or you can think about like the walking of a drunk person. If it goes to the right or to the left, so the probability that it goes to one side or to the other, also this is how you probably will come out. I don't know if you have a Lama's house this year. This party is well known about the parties, and we are expecting the students, like the organizers, they are responsible for the events, the parties is like responsibility of the students, okay? But we are very serious about it. So the students have a big responsibility in this event. You don't think like, I will go to the beach and it's everything fine, just fun. No, you have to worry about the parts, because as like the lecturers, the organizers, and all the professors, they want to go to the parties as well, okay? But going back to the random walk, so if you go to one side or to the other, the probability doesn't matter. If you give a step to the right or to the left, the next step, what will be, it doesn't matter. So what is connected to this Markovian stochastic process is this idea that the future evolution just depends. Yeah, I know. On the present state. And non-Markovian, I have a dependence with the past. So I want to have the same idea here, and as I said, I'm using the maps, the CPTP maps, to describe the evolution of my system, and I want to recover the same idea here. So I will then define as Markovian and non-Markovian if my map is divisible, oops, no. And as I said, if I have this, then if I know the state here, I'm able to tell you what is the state in time t. I don't need any information about the state in row 0. But if the map is not non-divisible, I will say that this is non-Markovian. And then I have to see the implications of it. So then just to finish it in my last 3 minutes, one example of a Markovian dynamics is, well, I can just think about a qubit state, okay, Bloch sphere. I will start with my qubit in the 0 state. And the recipe is just, I give some rotation every time step. I'm discretizing my time, okay, just to make it simpler. So I'm just rotating it in 15 degrees and so on, so on. So this is time 0, time 1, and then in time n, I am in this position here, and I can ask you, what will be the position in time n plus 1? What do you say? Yeah, exactly. So if there is a probability to rotate 15 degrees, if there is a probability to rotate to one direction or the other, so it will be opaque. Either here or there. So here was type T. Okay? Tn. So I don't need anything about this story here, cha-cha-cha-cha here, to be able to tell you if I will go to one direction or the other. So Markovian dynamics. For a non-Markovian, I can think about another example. Which is, I start also with my qubit in time, in state 0. And it will be, the map will be the following. So if I have a qubit, I can use like photons and use the polarized degree of freedom of the photons. So H, the horizontal is 0, the vertical is 1. And I will put in the way of these photons some half wave plate oriented in a way that it will do a sigma X or a sigma Z operation, okay? But the photon can come here, can come there, so the probability that it will arrive in sigma X or sigma Z is the same. So at the end, what this will do is, so if I start my state in 0, 0, I will end up in half of the time it will suffer sigma X. What is the sigma X of 0? Oh. What is sigma X? It's a bit flip. Well, if you don't know this, I'm sure this will come. And sigma Z in 0?
And you say 0.
Yeah, it's the eigenvector of sigma Z. Well, I didn't explain this, but I always consider the computational basis, the eigen 0 and 1, the eigenbasis of sigma Z. Okay, just Schneider is already looking like with some anxious to me. This will go to identity. It's easy to calculate this. But then the next time, I will just put the same plates. So this time 1, time 2, and in a way that here will be sigma X and here will be sigma Z. So at the place, like every time step, I'm putting half wave plates in a way that will be doing sigma X on the top and sigma Z on the bottom. So what will be the next state? Here. Wait. Yeah, this is true. So we'll see that if you just do this calculation, well, if I have sigma X times sigma X, this is just identity. If I have sigma Z times sigma Z, this is just identity, so nothing will happen to my state. So I started with 0, I go to identity to a maximally mixed state, and I go back to 0. So then I can make the same game with you, and I'm here in time n, and I ask you what will be the state in time n plus 1. What do you say? 0 if I know that I started in state 0. This is correct. It's 0 because I told you I started. But if I start with 1, the play will be 1, go to identity, and then go back to 1. So you need to know where you started. Okay? So this one, I think I'm convincing you about this non-Markovian dynamics. Another thing just to finish, I have chosen this example because I have a situation where I have started with 0, goes to identity, and then come back to 0 again. See, if I start with 1, you can do this calculation. It's kind of easy, okay? I start with 1, go to identity, and I go back to 1 again. So if I just compare, I'm starting with two situations that I have completely distinguishable states. Then in time 1, they are equal. There isn't any measurement that I will say that if I use situation 1 or situation 2. And then the last time, I'm getting distinguishability again. So this is what we will see in the next lecture, which is this, what we call this backflow of information. So you have some quantity, for example, distinguishability, which you start with full distinguishability, then in time you completely lose distinguishability, but after some time you recover distinguishability. So okay, this will be important to witness and also to explore non-Markovian dynamics in quantum information processing. Okay, that's all. Thank you, guys.
Thank you very much. Do you have any last questions for Nadja? One last question, at least. You know, when a professor asks you something, the probability that the answer is 0 is 50%. 0. No questions. So we'll have the coffee break now. We have half an hour of break. You can come to register, but please do not make a big queue because you are like 100 people to register. So keep calm, come, and then you have the break in the lunch as well, which is a big break that you can come and register. So we have coffee outside.